Wouldn't it be great to be 22 again? Oh, man.
I'm not 22 yet.
21's the only age that matters, maybe, yeah? So, I was reminded. So, if you look at the Cameo, which I'm just chatting, so you can chat amongst yourselves. So, if you look at the Cameo that is for this class, that was my first ever job as an engineer, same age as you. On this date, as I get older and more nostalgic and realize that I've got more days behind me than ahead of me, you guys are the opposite, hopefully, I look every day at my photos to see what I was doing on this date in the previous years. And so on the 20th of January in 2020, we're just about to be slapped in the face by COVID. I ended up going to Seoul, South Korea, to do an evaluation on a program in Seoul National University, and flying there out of Chicago, probably could have been DC. You fly over the poles, and I flew over the first site that I ever spent my time on, where that picture was taken of Mukluk Annie, which we'll go back to sometime, and it was here. And I flew over it, and you can't see very well, but if you want to know where it is, I guess I could do that. Why won't it go smaller? Oh yeah, I'm fine. Won't go at all. So. Yeah, I see. Why won't it do that? There it is. So, my first job, I turned up at our office at 7 o'clock in the morning with all my worldly possessions that I was traveling with. I went for a leak, and my boss took my bag into the apartment suite. He said, "Why don't you go out and pick up an alarm clock and some warm clothes?" This is Calgary in February. So I did. Didn't quite understand it. Padded coveralls, thermal underwear, socks, down-filled hard hat liner. And so at 3 o'clock in the afternoon, he drove me to the airport in Calgary. I caught a flight to Edmonton, about 300 kilometers north. Stayed there overnight, and then the next morning caught a flight on the Tuesday morning at maybe 3 or 4 o'clock in the morning to Yellowknife, and then to Norman Wells, and then by 8 o'clock the next morning, 10 o'clock the next morning, on the Tuesday, after starting on the Sunday, we're standing on 3 feet of river ice on a drill rig, which is the photograph that you see on the Cameo. So this is my very first project. This is Norman Wells. If we go back, does it go back to this? I guess it doesn't. If you look at this is in the summertime. So this is a small town on the Mackenzie River. It's almost just south of the Arctic Circle. Mackenzie River is a kilometer-wide river, maybe a couple of meters deep, flowing into the Arctic Ocean, the Beaufort Sea in northern Canada. And in the field season is wintertime, when everything freezes. And this is a drill rig that was set up on these things that didn't exist then, and they're little islands, little artificial islands in the 2 meter deep river, which have on them drill pads. So this is a petroleum reservoir in northwestern Canada. The Allies were worried about the Japanese coming over in the Second World War. They occupied some of the Aleutian Islands, and this was a worry. But it's a very shallow reservoir. You know that reservoirs are anticlines that cap the fluid rising up, just like NAPLs. Lighter than water NAPLs float to the top and get trapped under this capillary trap. And then if you want to recover them, now you drill from the bank into the middle of the river and then suck it out. But that technology didn't exist at this time, so you build some artificial islands in the middle of the river. Each of these islands is a drill pad, just like you'd see in Pennsylvania, that goes down. I can't imagine it's more than a couple of 100 meters, a couple of 100 meters deep to the reservoir, and then you take it out. And in the winter time, this is what it looks like. You fly out on a 737. The front half of the plane is for passengers. The back half of the plane is cargo through the whole plane, not just underneath it. And these are those islands that I just happened to be going across on the way to Seoul, I guess, 6 years ago now, today. Almost today actually. I left Seoul on the day of their first COVID case. I think it was the 20th of January, 2020. So, oh, to be 22 again. Not to be. There you go. So that's preamble.
Someone came on the radio the other day, and I felt really sad because I actually related to it.
A song on the radio?
Yeah, Taylor Swift 22.
Oh, were you a Swiftie then?
I didn't realize that I used Swiftie was highly applicable to that.
Swiftyism isn't de rigueur these days, is it? I'm guessing.
I'm somewhere in between kind of knows the lyrics to
Fine.
not really.
All right. Okay. I don't know why it does that. Perhaps it's a bad connection. Okay, are we ready to roll? Okay, I was quite pleased with myself. I managed to muddle through everybody's names and putting everything online last time. Actually, I think there's only one person who wasn't here. I think so. We'll do that again rather than pass out the sign-up sheet. We started talking about the lighter and denser than water non-aqueous phase liquids. I don't think you have this figure, but it serves to make a point as we recap perhaps some of our ideas from last time. So this figure is no different from the movie you looked at, and also the cameo that we showed that shows a chimney of smeared material going down and then catching itself in a supported as a puddle, if you like, on a capillary barrier for these denser than water fluids. So this is just showing the same kind of behavior. You spill something on the surface, there's a water table which is saturated below. If it's denser than water, it will find its way down through that because it will sink, just like sinking in the swimming pool. It doesn't matter that it's a porous media or a fractured media. And as it goes down, it will leave this smear, if you like, which we could describe in terms of what we called saturation. And it will accumulate where it can't go any further if it reaches that. And it will accumulate basically on a lens of a capillary barrier, and it will accumulate as a puddle, basically a puddle if it was in the surface. If those capillary barriers with small pore sizes exist higher up in the stratigraphy, it will puddle there and it will roll off the side and keep on going down. And depending on the architecture of the subsurface, you could imagine that it could do that at all these different stages. All of these dark red parts represent something where there's something stopping it going down, and it will tend as a result to roll off the side. It's important for us because all of this is below the water table. If water is flowing below the water table because of the gradient of that water table, then there's flow, in this case, to the right-hand side. So the pristine water flowing from the left-hand side will pick up dissolved components and carry it downstream and create the plume that you're playing around with on your first assignment right now. So that's kind of the big picture that we're looking at. So we said that this behavior is controlled by capillarity, bless you, and we looked specifically at the idea of if we have a capillary tube, the venometer, you put it in a fluid. If it's water, the surface of that is water wetting, then it will rise up to the surface, and it will rise by a capillary height rise, which is h sub c, and that rise is proportional to the interfacial tension of the fluid and the material. inversely proportional to the diameter of that pipe, tube, and controlled by the unit weight of the fluid, which is pulling its weight down. So this would be for a water wet component. We talked last time that a water non-wetting one would look like this. Mercury would look like that. We didn't do it for a fracture, but in the picture that we showed, the movie we showed, when they dumped this red stuff from the surface, it went very quickly through some natural fractures. So you could imagine that the height rise, if you took two parallel glass plates and put it in the fluid, that you'd also get a height rise in here, and it would be given by proportional to the interfacial tension and inversely proportional to the separation. This is the full width of this. This is 2R. I guess it's a slightly different relationship. We also looked at what the saturations would look like, but we can go to that in a second. We defined a behavior in terms of what we called a capillary pressure. And capillary pressure is just the difference between the pressure in the non-wetting fluid and the pressure in the wetting fluid by convention, non-wetting to wetting. In our system, if this was water and air, then the water would be the wetting fluid on this plate, and the non-wetting would be the air. Some oxygen, but mainly nitrogen, right, in air, 10% oxygen. And so the idea is that the pressure in the non-wetting would be this, and the pressure in the wetting would be in the water, right opposite each other on this boundary. And the fact that this boundary is a catenary, fancy word for what a suspension bridge looks like. Suspension bridge is pulling down on something. You can imagine the cables in suspension bridge are in tension. This surface is in tension. And the fact that it's in tension means that if you resolve vertically, it means there's a different force, pressure on either side. That's really what we're talking about. And so that difference in pressure is between the non-wetting and the wetting fluid. And you can think of that difference in pressures as being the unit weight times the height rise in this. Unit weight of this fluid, the liquid. And we'll use that today. And we looked at, we defined some terms. So that's what we need for now. Okay. So what we'd like to do is, if I go back to this, I think we didn't look at this either, but let's look at it now. So this represents the same same behavior we talked about last time. So far we've looked at the capillary tube and what the height rise is in it. We talked about the saturations of different components in the pore space. And we could define the saturation so that if the pore space is completely filled by one fluid, that's 100% saturated, 1.0. If it's 0% saturated, if it's all another fluid, then that's 0. If it's 50% air and 50% water, it's 50% water saturated and 50% air saturated. So if you look at an aquifer, this is a bead pack. Below this green line, these are very fine diameter beads. These are much coarser diameter beads. And so if you put this DNAP, this non-aqueous phase liquid in here, as this red liquid, it will travel down until it can't get access into this smaller pore throat. And so this kind of looks like what our reservoir would look like. Here, if you took a portion of the reservoir, this would be the saturation of water would be 100%. The saturation of the non-wetting fluid would be 0%, right? Because there's none in there. Likewise, that would be exactly the same as down here. But from what we talked about funicular and pendular saturations, since this area here was originally saturated with water, and the water loves to stick onto the beads of glass, then water will be present even where it's all red. And so we don't know what those proportions would be, but it's not going to be 100% saturated by the non-wetting fluid. It may be 80% saturated. and the water that pre-exists in there will still be at some percentage. It doesn't matter what these proportions are. Likewise, if we look anywhere here, we'd see the same behavior. Ahead of where these little fingers have reached, this would be 100% water, but in here this would be some proportion of water and NAPL in different proportions. And so what we'd like to be able to do is say something about how can we predict exactly what these magnitudes of these proportions might be from knowing something about the characteristics of the system, which is really in terms of the wetting characteristics. So that's what we'll try to do today. So what we would like to do is we think that in the same way, this seems like a blunt object. In the same way that we can define the height rise that would happen for this, we can multiply that by unit weight of the fluid, and that would equal what we'll call the capillary pressure. Capillary pressure we already defined today as being the difference between the pressure in the non-wetting fluid, by definition, and the wetting fluid. Air and water, or NAPL, NAPL and water. And so clearly, if we look in here, and we look at any point here, there'd be a single saturation of the non-wetting fluid here. It'd be 100% non-wetting, 0% wetting. Here, this would be 100% wetting and 0% non-wetting, because there's no air here. But we think that in real geologic media, we can go between those. And so our question is, how do we define what the saturation is as a function of the characteristics of the system? And so the characteristics of the system would be as a function of radius, as a function of the interfacial tension, whoops, geez, as a function of the radius, interfacial tension, that's sigma, the unit weight of the fluid, I suppose, and whatever other properties we have. So we like to figure out what this saturation distribution is. And it will turn out that we can most readily define it in terms of this capillary pressure. So that's kind of the journey we want to go on today. So the first step is to see exactly what a relationship might look like that links these two things directly. And so although we've already made the case that we can define this little behavior in terms of little round capillaries and other geometries, we're going to use something else to do that. Okay? I just want to jump back to the end of our notes from last time. I didn't post the video from last time because the video turned out to be recording the hidden screen here, and so it's just my face talking all the time. I didn't think that might be particularly appealing to you, so I didn't post it. So this is us today. Just two things to finish off. This is where we finished off last time, with the idea of this capillary potential. We talked about capillary pressures, which we've talked about again. If we wanted to do these simple models, we could also choose a different geometry. Instead of capillary tubes being a porous media, the pores in the media being a whole series of these little capillary tubes, you could think of the porous media as two grains in contact. And the water, which it's hydrophilic, the water loves this, it's water wetting, the water wants to stick to these. You can also calculate what the capillary pressure is in this by looking at the shape of this meniscus. So it's just another way of looking at it instead of capillaries. And that way of looking at it is in defining what the capillary pressure is in terms of the difference between the non-wetting fluid, which is P2, and the wetting fluid, which is the water. So this is the water, and the air would be the non-wetting around it. And in the same way, we made the case that in the capillary, this catenary that sits on the top, the suspension bridge, is what makes the difference between the pressure in the air around it and the water just below that surface. You have exactly the same process here, except the curvature is different. It's in kind of two planes. Two of these, you have this pendular saturation. We talked about a pendant. It covers the grains to one molecule thickness, but in the area where it's accumulate, it's in this ring, this torus that goes around it, a donut in other words. And this donut, if you look down on it, has a curvature. It's curved as a circle, and I guess it's the inward surface is inwards. But there's also a different, so there's a radius of curvature as you go around this in the horizontal plane, but there's also a radius of curvature as you go around it in the vertical plane, right? In the plane of the bead that joins these two grains. And the only point I want to make is that we can define a capillary pressure in the system, which is the difference between the air pressure on the outside here and the water pressure right on the other side of that surface in terms of the curvatures of those two radii. Happens to be additive, and it ends up being an equation. It's called the Young's equation, and it allows you to calculate what the capillary pressure is as a function of this saturated geometry rather than individual capillaries. It's not very important to us, but it's just a way that people have looked at this. And the main take-home point is that there's a different pressure on either side of this boundary. Even though in statics we say that if you have a flat boundary, the pressure acting downwards has to be the same as that acting upwards. Because it has a curvature, it can carry an extra load, just like a suspension bridge. Okay? Not going to talk about that. And we could do, if we now go back to the single capillary, since we think that fractures are important things in these systems, we could do exactly the same calculation to calculate what the height rise would be if you put two parallel plates into fluid and look at the height rise between them, which it will. It's just given by this expression here. It differs by the other one. We had 4 times interfacial tension, unit weight of the fluid, and the radius in the other one. It's just slightly different. So the point is we can define exactly what these entry pressures would be. What we'd like to do is be able to now relate it not to the fact that we have 100% saturation here of one fluid and 0 of the other, and likewise in the liquid we have 100% saturation of water and 0% of the non-wetting. We'd like to see what these areas are where we have partial saturations. So we'll talk about that. And just to make things perhaps more complicated, this is the recap we've done with a bit more. I'll come back to these, but I'll go straight to this last one. And so I'll scoot forward in my notes a little bit to be able to do this, because I decided it's much more logical to do it this way. And talk about the apparatus we might need. So I think it's at the end of this Thursday's class, if you're working on notes. Pretty straightforward, so this is the idea. So maybe what we could do, don't know why it's frozen on me. What we could do, here's the experiment that allows us to make that determination. What we'd like to do is we'd like to make a curve which relates capillary pressure in some way to saturation. And so if we do a graph which relates to saturation, and so this is saturation of water, I'll call that SW. So this is 0% saturation of water, 100% saturation of water. And saturation of the non-wetting fluid, this has to be the opposite. So you'll recall that saturation of water is the volume of water divided by the volume of the voids. by definition, right? So it's 100%, if the voids are 100% water saturated, it's 1, or 100%, likewise 0. So we want to be able to figure out exactly what this is. Don't draw a question mark there, but that's what we want to do. I've lost my favorite color because I was using white in the last class. What's my favorite color? Red, I think. So, we have a core. So this is the idea. You take a core, it's saturated with water. So it's 100% saturated with water, and you put it in this apparatus. So this apparatus is a chemistry beaker that sits on a frit in the bottom. This frit allows water to go through it, but the pores are small enough that it doesn't allow a non-wetting fluid to be pushed through it. So the non-wetting fluid is, say, in this cross-hatched region here. Within the core, we have the wetting fluid, which is water. So water in the core, this is a core, and surrounded by non-wetting fluid. It has a frit in the bottom that will only allow water to go across it, so the oil doesn't go across it. And you set this up against a gas cylinder so you can put pressure on this. So the pressure you apply to this allows you to generate a capillary pressure, which we define as the pressure in the non-wetting fluid minus the pressure in the wetting. So before we apply a pressure here, this essentially is there's no fluid weight on it, so it's essentially at atmospheric pressure. This is the brine that also saturates this sample. It's saturated with brine. It's brine because it's a reservoir, an oil reservoir rock, which tend to be brines, and this is from the petroleum literature. And this brine is a U-tube, so that the pressure within this water would be equal to this if it's open to the atmosphere, right? So this is 0 atmospheric pressure here, which would be the same as 0 atmospheric pressure here. It's completely saturated with water, and it has only atmospheric pressure acting on this system. So now, what you do is, in the non-wetting fluid, you jack up the fluid pressure. You increase it. So you apply a nitrogen cylinder here and you push it in. So as a result of that, the pressure in this core correspondingly increases, and so it goes up to some amount and it compresses. If the pressure isn't enough, so it pushes into the pore space of that core, then the saturation of the core won't change. It'll stay on this line. Fine. So you push up the pressure some more. And maybe you go up to here, and maybe that's enough pressure that it starts to invade. So you could imagine that the water that's trying to get into here will have these little feelers that will go into this. These will be the biggest pore throats that it can get into the pore in. So by definition, the 100% saturation of water in here is going to go down, and the saturation of the non-wetting fluid is going to go up. So you've jacked up the pressure to this slightly larger capillary pressure. You haven't increased the pressure in the water because this is still the height of the water column here, but you have increased the pressure in the surrounding region here. So this has gone up, so the capillary pressure has gone up. So this is increasing, and so this is by increasing. So you get to this point. You start to invade the sample, so over a little bit of time, you'll move to this new point, and these little fingers will come to an equilibrium. So now you go back to your sample. You again, let's increase the pressure to this amount. As a result of that pressure increase, some more of this non-aqueous fluid will go in here, and as a result, over time, it will come to some equilibrium. It won't keep on changing because it's held by capillary forces. And so you keep on doing this until your figure looks like this. And so these vertical and horizontal portions only represent the transient change. Pressure going up and the saturation changing to be in balance with it. And so the capillary pressure versus saturation curve that you get will actually be joining up the locus of these points here. I didn't do it very well, but that's it. So now, I guess you find yourself, if you did this last one, to be here. You sit here. Maybe you keep on going off the page. So you're here. So now you do the opposite. Now you drop the pressure. I guess, okay. The other thing is that as you pump these red and blue stringers into here, you're filling up with the non-aqueous phase liquid. You're having to push out the water. The water can only get out by going into this brine tube, and it can only change this level by changing the level here. So this won't change the pressure very much in here compared to these pressure changes, but it will change the level. So this change in volume allows you to calculate what the change in volume here is. So this change in volume allows you to capture the saturation change, right? So this is delta S, this is delta PC. So you can calculate delta S from the volume that's expelled from the core, and you calculate PC because you're changing this pressure, you're applying it. So now the opposite is that now you back off this pressure by dropping it. Perhaps I could do it with a different color. So if you drop the pressure by this fuchsia color, then you do the opposite. So the pressure gets dropped and the saturation responds to get a new point. So that means now with the pressure, it'll suck this stuff back in. So this will come back down. These little fingers will retreat as it goes back into the oil surrounding it, and you go down the same points here. And again, if I find the curve, I just want to join up these dots. And so this is what we would call as a capillary pressure versus saturation curve. CP versus saturation curve. And what it does, it tells us exactly what the saturation of this looks at any particular capillary pressure. And that's kind of useful to us because as we go down in a column of fluid, whether it's in a swimming pool or in a porous medium, you can always calculate from the height below the free surface that you are at what that pressure would be, and so you can find out where you are on this vertical ordinate. If you know where you are on this vertical ordinate, you can go across here, and I'll use gray. If you know you're at this particular capillary pressure, you will know exactly what the saturation would be in your system. It's ambiguous because it could be this value here, or it could be this value here. And it's kind of a complicated relationship because this is, these curves are wetting and drying curves. And that is because we go up this curve. If I draw an arrow here, I think, as I recall, this is the drying curve and this is the wetting curve. It's drying because it's becoming less water wet, and it's wetting because it's becoming more water wet. It's more saturated in water. So not a very pretty figure, but you get the rough idea. It's the easiest thing to see. So we'd like to be able to not rely on these capillaries where it's either 100% water or 100% air, but where if we take this whole, certainly if you look at any particular microscopic point within a pore, it will only either be NAPL or water. But if you take the whole continuum sample at whatever the saturation is, it's some average saturation for some average capillary pressure, whatever that is. And this is what we end up with, right? So that's it. So we can create that curve because We always know what the capillary pressure we're applying is because we're applying this nitrogen pressure to the fluid around this. And we know that the water pressure is roughly atmospheric. Hasn't changed very much because there's no super high column of water. And we can always calculate the change in saturation just by measuring the volume change out of the sample. The only place where that volume can go is through this frit and into the manometer-like thing. And so calculating a height rise multiplied by the cross-sectional diameter gives us a volume de facto, right? That's it. So it's easier to show that. So that's exactly what these curves are here. Do I want to do that? What am I going to do? Yeah, I'm going to draw it. I'm going to draw a curve here. So I think it's easier sometimes to draw these things and put on the important points. So if I drew a better picture here of what we have. See how good my curves are. Well, that's not bad. That's pretty good, even if I say so myself. Entry pressure. Sometimes called the bubbling pressure. Not because it's boiling. This is saturation of water. This is the saturation of the non-wetting fluid. So this would be 0. Let's call this 1 or 100%. Should make sure this is called a drying curve. This is called a wetting curve. This is SW0, SNW0. These are the irreducible. Is it an I or an E? I can't remember. Irreducible saturation of water. And of the non-wetting fluid, or the wetting fluid and the non-wetting fluid. And these are called scanning curves. Is my writing legible? Yeah, maybe. So, yeah, that's all we need. And so we can talk about what physically that means. Remember, if we go back, we talked about the ideas of funicular saturation and pendular saturation. And so this would be for a water wet. Sand or aquifer. Okay, I'm going to come back to this, but I'm going to just jump up here. So remember this figure here. So this work represents the stippled, this cross-hatch to the grains. The non-wetting is the black, the white is the water. And so if we start off with it mainly filled with water, the oil is present at a very small concentration. It's at funicular saturation. The only way you can get this bubble of water out is by pushing it through with the water as you get it from one pore throat to another. If you put more and more oil in this system, we went the other way because you start off with an oil-rich reservoir and deplete the oil. But if we go the other way and start putting oil into the reservoir, then the oil will make these little bubbles grow until they take up the whole pore and leave just a monolayer of water all the way around this grain, and also this pendular saturation around where the grains sit. We saw it in the diagram we looked at today for the 1/r saturations, and that is you get a ring around it, and it has a curvature in this way, and it has a curvature in this way. And so that's exactly what we have here. So these correspond to the axes, the saturation axis on the bottom of our system. So this would be on the left-hand side, right? 10% water, 90%, 10% water is on the left-hand side of our figure. 100% water or 90% water is on the right-hand side. And you see exactly what this relates to. I guess I could draw it. Perhaps I could screen capture it and move it. So right here, this would be the grains. With a blob of oil in the middle. This is funicular saturation. And this would be the opposite. You would have these little pendular saturations around these contacting grains, and it'd be existing somewhere here, right? This is just the spectrum of different saturations. 100% water, nearly, 100% oil on this thing. So that's physically what we're representing. So the reasons for these irreducible saturations is that at some stage you can't get all the oil out, basically. You have this bubble that's left in here and it's not going anywhere. It's floating in the middle of water, but you can't get, even if you pump more water back into the system, you're still going to be left with this irreducible saturation, which is this, where this curve contacts here, which is this. And likewise, if you keep on allowing the water to drain out by pushing in, by going in this direction. So in going in this direction, you're increasing the saturation of the non-wetting fluid. So you're pumping oil into this. You'd go along this curve here, but you can't get any further than this. At this point here, you've got as much oil in the system as you can. There's no more room for any more. You have this little pendular saturation around the contacting grains, and a coverage on the grain as well, which completely covers the grain. So this physically represents this. And importantly, these represent a unique capillary pressure. Kind of. And so if you know exactly what this saturation looks like, I say it's a unique saturation, but it's kind of ambiguous because it could be either of these, right? So if you see in the field a saturation that looks partway between here, that's on this curve here, by definition, it could be, if it's drying by forcing water out, it would end at this point. And if it's resaturating by putting water in here, by wetting curve, it would have this particular saturation. And if you don't know the pathway by which it got there, you don't know which one of these it is. So that makes life a bit complicated. So it's important to know these regions here, because these are regions, this is the amount of oil that you can't get out. No, sorry. This is the amount of water you can't get out. And it looks like it's maybe 20%. 20% saturation of water and 80% saturation of NAPL already in there. And this is the amount of oil you can't get out. So this is probably 20% non-wetting. Wetting. So these represent kind of no-go areas that you can't get the oil material out. Big deal for us, because if you have something that dissolves at 100 parts per billion in water and is carcinogenic at 5 parts per billion, then it will dissolve in that concentration in the water and keep on supplying it forever and ever, because even with a very small percentage of saturation. So that's a big issue for us. If you end up stopping at this particular saturation and then increasing your capillary pressure, then instead of going directly upwards, you'd go along this so-called, actually it's the wrong one to do, let me do this one. If you increase the capillary pressure here, instead of going up vertically, you'd go on these scanning curves, which is hysteretic. And so the fact that if you go up on this curve but come down on this curve, this hysteresis, means that it matters how the surface was previously wetted. And one good analog of that, I think, there's a picture of it somewhere else, but if you imagine a drop of rain on a windshield, you can imagine that the drop of rain as it travels down the windshield might look like this. The front here that it sees has already been wetted by the part in its trailing tail behind it, has not yet been wetted by that. This part here has already been wetted by the bead as it's traveled across here. So the contact angles at the upstream and downstream edge are different because they have different histories of wetting. And so this is the same. This is water being forced out and being replaced by oil to get more oil in the system. And then this is water being pushed back in to displace the oil. So it matters which pathway you go on. And the reason these aren't the same curve, you don't go up one and come down exactly the same curve, is because the history of wetting on that surface makes a difference in that behavior, right? So that's a very important figure that we'll use. It's our so-called capillary pressure versus saturation curve, which we've talked about how to get experimentally and how we'll talk about these different realizations. Okay? All right? What else can we do with that? It turns out that you can apply Buckingham Pi to this, and you can do dimensionless analysis, which of course is non-dimensional, and you can describe the behavior of this system. And I didn't define it, so this is called the bubbling pressure, so-called bubbling pressure. There was a picture of this on one of the previous slides. If these are the two grains, and this is a blob of oil that you have, this is the delta capillary pressure you have to apply to push this finger through this pore throat. So in this core, when we have it saturated with water and we at atmospheric pressure with oil all around it, none of the oil goes into it. You increase the pressure, maybe none of the oil still goes into it because it hasn't got big enough pressure to get into the smallest pore throat that exists. But at some capillary pressure, some overpressure of the oil, it will be big enough to invade. And that's exactly what happens here. At this bubbling pressure, or capillary pressure 0, entry pressure, the difference between the pressures in the water and the bigger pressure in the oil outside is big enough to have a bubble go into the biggest pore that you have in your core and make this finger. As you keep on increasing the pressure along this axis, progressively it will go into bigger and bigger pore throats which exists on the boundary of the thing. That's really what's happening here. So this is an important behavior for us. So if the capillary pressure isn't bigger than this bubbling pressure, which is a function of the rock, it's a function of the pore throat size really, and the fluids which you're trying to get into it, this would describe when a capillary barrier works as a capillary barrier. So you have this clay, really small pores. The oil comes down and sits on it. If it's only a very thin layer, there's no supernatant pressure acting on that column to be able to push it into that small pore. If the depth of it builds up, now the pressure in the bottom of this column is just rho GH. Now it's bigger than the pressure acting in that pore, and at some stage it'll be big enough to go into the pore barrier. So this is an important parameter for us to know when a capillary barrier will act as a capillary barrier. Is the pore size small enough that it will stop it going? So that's something that we'll play around with this. If you want to, you can do dimensional analysis. So the dimensional analysis would be by taking an idealized piece of aquifer, which you put a whole bunch of capillary tubes to represent it, like a Swiss cheese, but with tubes instead of the round holes. And if you then look at the pressures you have to apply to push it into this capillary barrier, you can also relate this to define the permeability. The permeability is a function of the radius of the pore. Actually, it's the radius squared. And so if the ability to flow fluid by Darcy's law, velocity is equal to permeability, viscosity, and the pressure gradient we apply, just in a single fluid. So this defines what the transmission characteristics are of a porous medium, and we can relate it to the size of the individual pores in here. From our ideas of taking a capillary and putting it into water, that also is a function of the radius of the pore. So maybe if the behavior to invade is a function of the pore radius, what we could do is we could measure the permeability of something, which is quite easy to measure, relate that to the pore radius of that porous medium, and then use that pore radius to calculate what the bubbling pressure would be. PC0, right? PC0 equals PB, right? In other words, this value here, which is important. And so it turns out you can do that. We won't do it today. But the end result of that is that you can non-dimensionalize these curves in terms of saturation between 0 and 100% water saturation, 0 and 100% non-wetting saturation. This is the irreducible saturation of water. But the vertical axis now is defined not in a capillary pressure, which is equal to the non-wetting minus the wetting, but is equal to some function of that. And this J function is just the capillary pressure but multiplied by some other terms. And the other terms are divided by the interfacial tension and multiplied by permeability and porosity. They're all defined here. And so you can check that for dimensionality. It's by definition a non-dimensional term. So capillary pressure is in newtons per meter squared. I think interfacial tension is newtons per meter. Permeability is in meters squared. Porosity is in nothing. And so the square root meters squared is meters. And so this meter and this meter combined, so it's the newtons cancel out, the meters cancel out. Meters squared cancel out. So this term, this J function, a Leverett function, is non-dimensionless. And so what it does is it allows you, if you know that the entry pressure is always when this function is equal to 0.3. Just works out because of the geometry of this. And so if you know that when this term is equal to 0.3, that this represents this point here, if you want to know what this bubbling pressure is, then you just need to measure the interfacial tension of the fluid you're pushing in, measure the permeability of the porous medium, its porosity, and you have everything to be able to calculate this as a function of this. So it's a very convenient way to do it. And so maybe we'll derive it later on, but that doesn't matter. But the point is you can get this very important parameter. You could also relate it just to the diameter. What else do we need to know? We could also, these are kind of complicated figures. You notice here also that this is slightly different to the one that I drew. And that is that it misses this exclusion zone here. I guess it doesn't. It just doesn't have this line on it here that does this. But this represents this exact same behavior. What we might also be interested to know is whether we can describe this kind of strange curve in a more diagnostic way. And so what we might do to do that is we could ignore this part of the curve here, take only this curve for the drying, so-called drying curve of the liquid, as it starts off liquid saturated and becomes progressively, you could think about pushing air into it, so it desaturates and becomes less saturated with water, and try and define this behavior. If we do that, then we do two things. This is the curve that we've just left. Bubbling pressure, saturation of water, completely unsaturated. It has this, we're just doing one limb. This is the drying curve. Maybe it comes back down here. This is the irreducible saturation of water that we can't get beyond. What if we drew this curve and changed it so that we drew it on this axis? I'm going to redraw this curve, but I don't know how successful I'd be. This is the same curve. It goes up like this, and it goes here. So let's take off this cross-hashed part here. We'll define an effective saturation here, which we'll take as being 0 and 1. And if we do that, then we can, instead of using this full range from 0 to 100% saturated, we're going to use this curve for an effective saturation, which starts off at 0 here and ends up here. So we can define an effective saturation by this. This is equal to the saturation. So this would be SW. This would be 0. This originally would be the irreducible saturation here. So really all we're doing is we're changing our definition of saturation to be able to cut off this portion of the graph and start at 0 here and go to 1 here. That's it. So if you define it in terms of instead of saturation of water from 0 to 1, we define it in terms of being effective saturation, which is 0 to 1, but only starts at this point here. This is 100% saturated. So if we redefine it in terms of a saturation, and we divide this through by the unit weight of the liquid. So by definition, this is newtons per meter squared over newtons per meter cubed, unit weight. So this is equal to units of meters or centimeters. And then we just replot this curve in terms of this effective saturation. I haven't done you any favors because it's also rotated, right? This was the effective saturation on the base, capillary pressure on the vertical. What we're going to do is just switch it through 90 degrees. So it's log saturation, so saturation on the vertical axis and capillary pressure over unit weight on the bottom. And I suppose the punchline is, if you plot this on a log-log scale, then this curved figure plots as a straight line. And that's convenient because this doesn't have a very easy to define equation, but certainly a straight line on a log-log plot does. It has an ordinate. So if you think about high school math, this is y equals mx plus c. This is c, and this is just m must be, I suppose, has to be multiplied by dy dx, right? Yeah. Or delta y. Just the gradient by definition. So this is dx and dy. So this gradient here of m and the intercept is exactly the same as this gradient over one cycle, which is lambda, and an intercept. The intercept is that saturation is equal to 1, which is fully saturated. By definition, where saturation is equal to 1 is the bubbling pressure. This is what we've called PC0 equals the bubbling pressure. I'll just scoot up here so you can see it, right? This term here. And instead of having this crazy curve, we just have a gradient of this. I guess, yeah, I'm trying to work out. We stop at 250, right? Got a bit of time. And so what you can do is then define the behavior of this curve. So the punchline is, this is the real curve that you measure, maybe using the apparatus we just talked about in the lab. You can convert the saturation from 0 to 100% in terms of just the effective saturation, which cuts off this part, which is the irreducible saturation of water. It's just by taking whatever the water saturation is and multiplying by these constant, or subtracting this constant value. This is a function of the core. It's a function of the material. So if you have an effective saturation, you can plot it in log-log space, and you get a straight line. And you can define that straight line by this equation on the bottom, which is SE is equal to PC over PB to the minus lambda. This is just this. And if you take logs of both sides, I guess you have this equation here. I can also do that. This is log effective saturation. Logs of both sides here is equal to minus lambda times log of the ratio PC over PB. Right? That's it. So it comes with a ready-made way for us to convert something that doesn't look so orderly to something that does. And it can be used then to do this calculation. These are two different equations. That's all. And so if we do that, you can use that to look at these. And this is exactly that transformation. So this now is a plot of capillary pressure. So these are capillary pressure versus saturation curves. Happens to be capillary pressure divided by unit weight of the water. This is effective saturation, S sub E, not very clear. And these are exactly the curves we talked about. This would be the bubbling pressure, PB for 4. And these are just those curves replotted in terms of effective saturation here and on a log scale here. So this is saturation of 1, saturation of 1, a small magnitude here as you go across here. Never reaches 0 on a log scale, obviously. And the capillary pressure versus saturation curve, which is, capillary pressure value here, and the capillary pressure value here. And you could surmise exactly what these curves look like. So this is a small bubbling pressure. This is a big bubbling pressure. Big bubbling pressure must be this curve here. This is where it reaches present at 100% water saturation. If you want to push oil into it, you have to increase the pressure above bubbling pressure, which is right here. And if you do that, you'll slowly saturate your sample, and it will move on this trajectory here, up here. And so the fact that the shape of this is shown by a very steep figure means that you have to provide a big increase in pressure to get a relatively small increase in saturation. So the gradient of this line directly represents that. It starts off with the biggest capillary pressure because it's sitting here, and this will be a steep line as a result of it, number 4. If you look at, say, number 1, I guess, this is the lowest bubbling pressure. It would be this one. And as you go up here, it changes saturation very quickly. So it moves down here very quickly, and it goes along this particular trajectory. And again, this represents the bubbling pressure for PB1, PB4. The bubbling pressure, I guess the most obvious one is that this one here, doesn't matter what the bubbling pressure is, but I guess the most obvious feature for this is that as soon as you get the pressure to go into it, it completely invades the whole sample. And so this would give you, for a given pressure, almost PB2, I suppose, almost all the sample is invaded. So PB2 is this one. And as soon as you apply a small increase in pressure in this direction, zoom, you invade the whole system, and you have this steep curves. So a steep curve here means it is shallow here. As soon as you exceed the bubbling pressure, it completely saturates the whole sample. So you could make some guess, I guess, about the composition of that core. All the pores in this core must be about the same diameter. As soon as you've got entry into one of them, you invade them all. You don't have to apply any larger pressure to be able to do this. This is the opposite. This has a few very small pores, and then as you try and invade those small pores, the other pores you invade get even smaller, and they get smaller quite quickly because you have to provide, spitting on my screen, you have to provide a big pressure change to do it. So that's it. Don't know if I want to say anything about that. Yeah, I think this figure is there. This is the figure we've already talked about, hysteresis. So that's it. So if you want to, I guess, summarize, perhaps good to summarize, I never usually do, but the idea is that this curve is an important curve for us. The ordinates on this curve are important. The bubbling pressure defines what pressure we have to apply to be able to push a non-wetting fluid into the system. We can define that in terms of the Leverett J function, which is useful to us, because by knowing what the permeability of that porous medium is, we immediately know what that is if we know what the fluids are that are going here. When we push air or a non-wetting fluid in the system, we go along a drying curve. When we stop changing the pressure, we retreat on a wetting curve. The wetting curve is where the porous medium spontaneously sucks in the water, even as the pressure decreases as we're coming down here, because it loves the water. It's hydrophilic. It loves the water, and it resaturates, but it can't resaturate all the way because we're left with a smaller bubble of NAPL sitting in the system. These boundaries represent the irreducible saturations. This is the minimum amount of water we can have in the system when we have pendular saturation. We can't get that water out. And this is the minimum amount of NAPL that we're left with in the system, a little bubble of oil sitting in the middle of the pore. And if we go part way along these curves and then change the capillary pressure, we go along these so-called scanning curves. And we have scanning curves because these two different behaviors are hysteretic. It matters whether it's losing water or gaining water. It does it along a different path because the idea of a raindrop on a windscreen, the order in which This has already been wetted in the past. This has not yet been wetted by the raindrop. And that's what is the reason for this. That's about it, I think. Yeah, I think. And I guess the other important thing is that this curve is a bit squirrely and it's not very convenient for us to use. But if we manipulate it a little bit by lopping off this irreducible saturation of water and recalibrate as an effective saturation and as a capillary pressure, albeit normalized by the unit weight of the fluid, if we plot it in log-log space, it transforms into a simple log linear curve that we can define in terms of the effective saturation and the capillary pressure. And the rest of the stuff is that. This explains that. And let's not do it today. This capillary pressure curve exactly explains to us what the saturation should be as we go up in the column. And so we said that we have this little plug of the non-aqueous fluid dropping down through, hitting the water table and keeping on going. We said something about there being a smear of this non-aqueous fluid along that surface. This allows us directly to be able to say the saturation of that smear as we go down through this. That's what we'll talk about next time. Okay. Brilliant, right? All right, perhaps not. So that's it. That's all we'll talk about today.